Welcome to module 10 of the course Ultrafast Optics and Spectroscopy. In this module, we will learn a simple quantum mechanical model for ultrafast spectroscopy. A description of basic ultrafast spectroscopy in which coherence is important begins with time-dependent Schrodinger equation. The one which we have taken here, this is one dimensional. The spatial dimension we have taken as x. So, the wave function depends on x and t, and the term coherence is invoked here. In the previous module, we have discussed kinetic rate equations for different excitation processes. In those rate equations, we haven't discussed any coherence effect. So, what does it mean by this coherence? A simple manifestation of coherence can be understood from following figure. Let us say I have ground electronic state and the system is in the vibrationally ground state, and I am exciting the system to the electronically excited state. In the electronically excited state, I have different vibrational states. These are electronically excited states. Now, when we undergo this transition with the help of a monochromatic photon, then we can excite from V equals 0, V equals 1, V equals 2, these are the vibrationally excited states. So, one can excite from V 0 of the ground state to the V 2 of the excited electronic state, and that is possible only when I have monochromatic excitation source. But when we are dealing with an ultrafast pulse, a short pulse, then we know that a short pulse will always have, this is intensity profile of the pulse, will always have a broad bandwidth. So, instead of a monochromatic excitation, we might have a number of excitations simultaneously. So, this is represented by the broad bandwidth, which means I will be exciting this vibrational mode, this vibrational mode, this vibrational mode, this vibrational mode, this vibrational mode simultaneously. This kind of simultaneous excitation gives rise to coherence effect, or we create an wave packet. What does it mean? This will be revealed very soon. We create an wave packet. Okay. So, any kind of coherence effect can be understood from time dependent Schrodinger equation, where H is the Hamiltonian of the system. Here for simple representation we have used one dimensional problem, and single particle problem we have only simple potential operator and the kinetic energy operator in one dimension. Now, what does it mean by this psi x? This psi x t, if we take, this is wave function, but if we take the modulus square of dx, then this represents the probability of finding the particle between x and x plus dx. In this regime, what is the probability of finding that particle? And if it is normalized, then we can write down psi x t dx equals 1 minus infinity to plus infinity over the full space. The psi x t modulus square is called probability density for finding the particle at position x and at time t. If I know psi x 0 at 0 time, if I know the wave function, then from time dependent Schrodinger equation we will be able to get a complete solution for the problem, which means any time I can find out x t, and once I know wave function, I will be able to find out the probability of finding those particles at a particular position and time. If we use then variable separation method, which can be shown very easily, one can separate this psi xt into its two different components. One can decompose wave function psi xt into its components psi x and the time temporal component. Temporal component here in the wave function is given as a phase factor. This can be proved with the help of variable separation method, and which we are not showing here. So, what does it mean? If we have this variable separation method, then we see that psi x t can be expressed as psi x, that space component, and the phase factor, time dependent phase factor e to the power minus I E t by h cut. E is the energy of that state. Now, if this is the general form of the wave function. If we have this general form of the wave function coming from time dependent Schrodinger equation, all we need to understand that we do not observe wave function experimentally. What we observed, all the physical observables are related to its density, which is this square modulus. And if we take the density, then the probability density is given by psi star, which is finally we get this. So, what does it imply? Probability density is independent of time. This means that probability density does not change with time. That is, there is no effect, there is no effective motion which can be observed. So although wave function is time dependent, corresponding probability density what we observe is time independent. So, however, if we look at the linear combination of the solution, for an example, instead of a single state, if we consider two states where I have this is psi 1 and this is psi 2, there are two states, and total wave function is represented as a linear combination of this plus this, both states together, then we'll try to find out what will happen to the probability density. Any linear combination of particular solution is also a solution of the time dependent Schrodinger equation. By forming linear combination of particular solution, each with its own characteristic time dependent phase factor, we only obtain the time dependence in the probability density. How? We'll see that. So, this is the first wave function. Here there should be 1 because it is associated with energy of the first state. This should be 2 because it is associated with the second state, and it is a superposition state which we create. Somehow we have to create a superposition state to get the time dependence in the probability density. So, what I get is that if we take the modulus square, then finally we end up with an expression like this, where this is missing here, psi 2 star x is missing. So, what we get is that in such a situation where I have wave function represented as a linear combination of two states, then in that situation the probability density will depend on its own individual probability density, plus there is a time dependent component, and this time dependent component will control the time dependent variation of the density. We note that this equation has three terms. The first two come from each particular solution associated with respectively 1 and 2 states, and the third term arises from an interference term between the two. So, this is an interference term which is coming, and this will modulate as a function of time. As a function of time, it will oscillate because this function, this phase factor, is an oscillatory function. This interference term is a result of having superposition of eigenstates with different energies a wave packet. and this is called wave packet. So, when we create an superposition state, we call it is an wave packet. It is not a pure state, it is a two states together, it is a linear combination of two states, and that is called the wave packet. Therefore, a wave packet, a superposition of states having different energies, is required to have a time dependence in the probability density, and consequently in other observables such as average position, average momentum of the particles. So, this is a very important realization in quantum mechanics. In quantum mechanics, if we have a pure state having only represented by its spatial and temporal phase factors, that pure for a particular pure state we cannot have a time dependence in the density, that, and because it does not depend on time, it will, the average momentum and average position of that particle will not change. But if we have a superposition state, we create a wave packet, then it will change. Now, we will look at the interaction, how to think about the interaction of matter with short pulse. For any interaction, light matter interaction work, we always decompose Hamiltonian, total Hamiltonian, into its without perturbation and with perturbation. The both components will contribute. So, H naught is Hamiltonian for the matter without the interaction, and H dash is interaction Hamiltonian interacting with the electromagnetic field of the pulse, which is represented by mu E, and E is the applied electric field of the pulse. We know how to represent such a pulse in time domain. Et equals At, that is the envelope function e to the power I omega naught t. Omega naught is the central frequency of the pulse, and At is the envelope function, and mu is the dipole electric dipole moment of the molecule. So, electric dipole moment of the molecule is interacting with the dipole with the electric field of the applied beam. Now, the task is following: we have to insert that perturbed Hamiltonian into time dependent Schrodinger equation, and as I mentioned before, this is the real part of the electric field, and that has been represented in terms of its complex conjugate as well. And we see that the total wave function, if we consider total wave function, so now we have a situation where the first state and this is second state, and when we are creating a state due to excitation by a pulse, we are creating a superposition of two states. So, basically our bandwidth is such a way that is exciting both states simultaneously. This is the bandwidth of the pulse, and that is why it is exciting both states simultaneously. If we are exciting both states simultaneously, then we can say that there is a coefficient for this expansion that is time dependent, and this is the phase factor for corresponding state. This is, we are calling it phi 1 and this is phi 2. So, and that is the way we get a superposition state. This superposition state here is created due to excitation by a pulse, and that is why we are representing the final expression and a tentative solution of that wave function is going to be superposition of these two states. So, all we need to do is that insert that expression into the time dependent Schrodinger equation, and we get, first we will look at the right hand side, this side, which is the time derivative of this function. If we do the time derivative of this function, we end up with this expression. Here we remind ourselves that time dependent components are this expansion coefficient C and this phase factor. Here also expansion coefficient and the phase factor, both are time dependent. That is why we are taking the first derivative with respect to the first derivative of those components only. And after doing that, we can rewrite this equation one more time, and we can, here also we can insert the same expression for psi is a superposition state. When we insert that, then we get certain value, because here this H naught, if it is employed on phi 1 state, we get the E1 multiplied by phi 1. That's time independence Schrodinger equation. So if I have H psi equals E psi, is something like that. So we are getting individual energies here. So this is also true here also, but we have missed this E2 term here. There should be E2 term, and if we keep doing it, then finally what we see is that on the left hand side I have a term which is equal to the term on the right hand side. So we can remove these two terms, and finally we get this expression. And in many occasions when we are dealing with quantum mechanics, we make use of orthonormalization condition to reduce an equation. What does it mean? If I have, let's say, phi 1 plus phi 2 equals psi, let's say this is an example. If I have this situation, a linear combination of these two states, then what I do is that I multiply this both sides with the help of phi 1, let's say. So this is the complex conjugate of phi 1, this phi 1. So I get this expression on the left hand side, and on the right hand side I get phi 1 plus phi 1 phi 2. If I do that, if I have this expression and if I do this kind of multiplication, then we can make use of the orthonormalization condition, where we will be able to simplify this expression. Simplify, because this is going to be 1 plus this is going to be 0, something like that. So and in many occasions in quantum mechanics, to reduce an equation, we make use of this kind of orthonormalization condition, and that's exactly what we have done here. We have two states, that's why we can multiply by phi 1 in one step, and another step we can multiply with phi 2, and then we get two equations, time dependent equations, where we are representing C1 as a function of time and C2, derivative of C2, as a function of time, these two equations. And we can remind ourselves that C1 and C2 are the coefficient, which means if I have C1 equals 0, then there is no population in the one state, and if sometimes if I have C2 equals 0, then there is no population in the C2 state. So all we are interested in is that how the population is building up, how we are building up the population in the first state and the second state, depending on what is the coefficient for C1 and C2. So this is the reason why we are interested in C1 and C2. And then if we insert this, if we insert this final expression for this part of Hamiltonian, then we get this expression, and finally we end up with this expression. This is just simplifying these expressions, and we get this. Now when we get this, this is the expression for C1, and this is the expression for C1, and we can further simplify it, and we can write down the expression for C1 like this, where this mu12 is nothing but phi 1 mu phi 2. That's mu 1 2. So what we see here is that this C2 has been taken out, so we do not have this C2 anymore here, and here also we have taken out this C2. We do not have this C2 here. Okay. So we get the final expression like this. This is suggesting how the population in the first state is changing due to the interaction of matter with a short pulse. And here we will take rotating wave approximation, where we will approximately say that this we are almost in resonance with this phi naught, and this is omega 2 1 is the difference, this one, this excitation, they are almost in resonance with each other. And if they are almost resonance with each other, then the term which will contribute to this is going to be this C2, and we are assuming here an unsaturation condition where we can approximately say that C1 population doesn't change almost, it remains to be the same. So we are in the unsaturation limit, and if we are in the unsaturation limit, then we get the final expression for C2. So these two expressions suggesting that in the ground state, the first state and the second state, we are creating a superposition state, and we are saying that if we have a superposition state created by the excitation of a short pulse, then we can say that the ground state population is remaining almost the same, and that's why it is 1. But C2 population is changing as a function of time. This is unsaturation limit, and C2 population, C2 value will depend on this integral. So this is a representation of how the population can build up. The population can be built up in the excited state as a function of time due to interaction with the short pulse. Now let's look at the creation of the wave packet. The Hamiltonian will be expressed explicitly in terms of nuclear contribution, electronic contributions, all the contributions are included. So here this one is electronic contribution, this one is nuclear contribution, this one is potential coming from interaction between nuclei and the electron. This one is nuclei, and this one is electron interactions. And if we consider adiabatic Born-Oppenheimer approximation, where psi can be expressed as this is a product of nuclear wave function and electronic wave function, then if we plug that in, we get this, and we'll be able to separate this to expression. This is pure electronic wave, component, and next one, this is pure nuclear, the contribution from nuclear motion. And if we then insert these contributions into the previous Cn equation, then we can say that this is proportional to mu 2 1, and that's an expression which we need to find that out. And mu 2 1 expression is given if we simply insert it and simplify the expression with the help of the identity operators like this, we finally get an expression for the excited state. What we get, this expression for the excited state suggests that the excitation at 0 time, so t equals 0, when just the interaction is happening, at that time the wave function which I have created is nothing but the ground state wave function of the ground state nuclear wave function. So what does it suggest? It suggests that, let's say at t equals 0 only. So let's say I have the ground state, which is represented ground electronic state, and this vibrational state is represented by this chi 0 0. this vibrational state, and we know that the wave function of this state is going to be, if it is simple harmonic oscillator, then it's going to be an Gaussian wave function. On the other hand, we are exciting the system to the electronically excited state, and with the help of an ultrafast pulse, and in that state we have a number of vibrational states, and we have assumed that we have taken linear combination of n number of states here. So, the final wave function, how does it look like? It will be a superposition of all states, n number of states we are considering, 0, 1, 2, blah 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 blah, n number of states we are considering. That's why we are taking n number of linear combination, and finally if we take the n number of linear combination, then this final wave function would look like just like the ground state wave function, which means that this wave function would be coming on this surface only, and this is called wave packet. So, we have created a wave packet in the upper excited state due to excitation by an ultrafast pulse. This wave packet definitely would evolve in time. Why? Because it is a superposition wave packet. The wave packet is created due to superposition of different states, and we know that the moment we create a superposition state, it will definitely, its density will definitely evolve with respect to time. How a wave packet will evolve on the potential energy surface, that's the part of discussion for wave packet dynamics, which can be very interesting to learn, although in this module we will not discuss that. We will just end this module. In this module we have we have represented quantum mechanical model, which can be very suitable for understanding, for the first time, understanding ultrafast spectroscopy, and we have discussed how an wave packet is created. And wave packet in its simple form is nothing but, when we undergo an electronic excitation with the help of an ultrafast pulse, the wave packet we create is nothing but the ground state wave function placing on the upper excited state. We will meet again for the next module.